In this video, we're going to talk about complex power. We're going to see the different components of the complex power. We're going to look also at at the the power triangle. Okay. So how do we get the complex power? We can use these two formulas. So we can use the voltage and current in RMS units, RMS values. Um, and we just multiply them. So voltage times the conjugate of the current. In the case of regular units, we can use the formula below, which is V times I conjugate divided by 2. And so the complex power has different parts to it. So we have the complex power, which is S, and it's a volt because it's a vector. We have the apparent power, which is the magnitude of the complex power. We also have the real power, which is the real part of this, the real part of S. We also have reactive power, which is Q, and it corresponds to the imaginary part. And then the power factor, which comes from um, the angle of the complex power. And so what do I mean by the real part, the imaginary part, and the magnitude and everything? So remember that complex power is basically a complex number. So mathematically, it's a complex number. And so we can display it, or we can find it in in two um, in two ways. We can display it in two ways. We can show it in rectangular coordinates, and we can show it in polar coordinates. So those are two ways that we can express it. And so whenever we express it in rectangular coordinates, the part that we get as the real, that's the real power or average power. This value that we get next to the J, that's our reactive power. In the case of polar coordinates, this value, which we usually call the magnitude, that's the apparent power. And then if we get the cosine of this angle, that's what we call the power factor. And so we're going to do an example. Okay, before the examples, let me explain the power triangle. So whenever we think about the S as a complex number, we can plot it in this is the real, and this is the imaginary axis. So this is our complex plane. So if you think of S as a vector, and this is capital bold S, you can think of the X component and the Y components of it. So if you do a triangle like that, which is our power triangle, you say the real part, that's our P, so we're going to label it P. So this is P, X is P, and then we have this is Q. So that's our reactive power. And then we end up with an angle right here, which is theta, and that's going to be theta of the voltage minus theta of the current. And I think that's it. So we have, oh, I'm missing one. I'm missing S magnitude, which is this one, right? So we can say the magnitude and the angle, that will be polar coordinates, or we can say the X or real component and the Y or imaginary component, which is this guy. And so in this case, when we have the Q that is greater than 0, we can say that it's a lagging PF. We call it lagging PF. Okay. We also have the case when our S is here. Down below, we have the real also, and we have the imaginary axis. And so we also have, in this case, we have S. Now we have an angle, right? And then we're going to have, now we're going to have P here. So that's here. So P. But we also have Q right here. And then you can notice that Q is less than 0. So Q will be negative. And we call that leading PF. Okay, so whenever that happens, that means that we have a leading PF. So now, what about the PF? What is PF? That's the power factor, and it's cosine of the angle. In the case that we have pure resistive loads, that means that Q is equal to 0. That means that the I and the V are in phase. That means that the difference is equal to 0. If we actually do cosine of 0, we get 1, which is PF. Let me do this properly. So we have the PF is equal to the cosine of the angle, which is 0, and so we get a 1. And that means that S is equal to just P, so we don't have Q's. In the case of pure capacitive load, we have the current leading the voltage. That means that Q is less than 0. And so we have a negative number. We don't have any P, so P is equal to 0. And in that case, we have the leading PF and a capacitive load. In the case of pure inductive loads, that means that Q is greater than 0 and the P is equal to 0. And that means that the I is lagging the B. And that's why we call it lagging PF. And that's why in the case of number 2 case, capacitive loads, we say I leads the V, current leads the voltage, and that's why we call it a leading PF. So one example, what would be S here? So S will be B times I conjugate. Okay, so first, what is I conjugate? So I conjugate is equal to this minus 44. So we just put a minus sign on it. That's the conjugate. So we have S, and this is volt S, is equal to 4 angle minus 10, and then times 25 angle minus 44, and I'm just gonna say that is milliamps. So just be careful with the units that we get at the end. So S bar, or just S, will be, let me see. So for that I get a 58.779 minus 80.99 J, and that's milli VA. Okay, because of that milli in the amps. And so that's one way to put it. And then I can also put it in polar coordinates. So I'm going to convert this in polar using the calculator. That will be a, let me see, where is it? 0.1 angle minus 54. And so what does this mean? This means that's VA. Okay. And so this means that I have P is equal to this, Q is equal to this, so it's a minus, S magnitude, apparent power is this one, and then the PF factor we can calculate using the minus 54. So we're gonna say P real power is 58.779 milliwatt, and it has different units. And in the case of the Q, we're going to have Q equal to minus 80.9, and that is going to be equal to V milli VAR, which are the volt amp reactive units. That's the name, volt amp reactive. And then we have apparent power, which is going to be S, magnitude will be 0.1, and that's also VA. And then we have PF factor, which is going to be PF cosine of minus 54, and I will calculate this. For that, I get a 0.588. Okay, and this is a negative Q, right? So it's negative Q. That means that we said which one? Q less than 0 was what? Leading, lagging, leading. Okay, so finally, so this is complex power. This is how you get the different parts of it. It's not very complicated, I believe. You you do the multiplication b times I conjugate, and then you can express it in real coordinates, and you can express it in polar coordinates, and you can get the different parts out of it, basically. And so this is all I got for this video. That's the short explanation of power triangle and how to get the different elements of complex power.